good. All righty. So we talked a little bit about feedback control. Last time we covered PID a little bit, and we're going to finish that up. And then we'll think a little more about pure pursuit, which is specifically tailored to vehicle navigation, right? Car navigation. Okay, so let's start by some logistics. Homework 3 is now out. Homework 3 covers PID control, pure pursuit, and some MPC. So you should be able to start it. I know there were some car issues that some of you had. Are they all resolved? Does anyone still have a car issue? No? Okay. And apologies about this LiDAR situation, but I think everyone got through it. LiDAR flipped situation. Okay. Quick quiz. Honestly, let's just skip the quiz. Um, I know a lot of people are at the seminar. So. Okay, so quick recap. I'll blaze through it. Tell me which parts I need to stop at. We talked about sense, plan, act, right? And we're thinking largely about control once you have a plan and a state estimate, right? And so specifically, we're thinking about feedback control. So a control system where you know the error between where you are and where you want to be, right? And so you measure the error between where you are, where you want to be, and try to take actions to minimize this error, right? And so we're trying to think of controllers that look like this, which gets a reference point or trajectory to track. You pick a particular point you're trying to go back to. You take the error between your current state and the reference state, right? And then you try to design a control law which minimizes this error. So it takes action so that your error becomes smaller, right? And so our focus today is going to be in designing this control law. So K here is a function that takes an error and gives you actions, right? And so we're going to be trying to design the form of K, which is going to work generically across systems and specifically for the car, right? So PID control, which we'll talk about, is a very general system. A general control law works across lots of systems, whereas pure pursuit is very specific to the car, right? And so we're going to start with PID control, and then we'll get to something specific for the car. And in general, we're going to think about a restricted setting where we don't change the throttle, we just change steering. And so if you remember last time, there was cross-track error and a long-track error. If you can't change the speed, you can't change the long-track error, you can only change the cross-track error. Right? So because you can only change which way you're going. And so what we're going to do is we're going to try and change the steering angle so that we minimize cross-track error. Yeah. Okay. So the basic basic design of a control law is you're trying to find out what U is dependent on the current state X and the error between your current state and the desired state, right? And the desired target. And you're going to do this with feedback, which means you're going to apply the control law. You're going to move a little bit, and you'll apply this control law again, right? And so whenever you think of a closed loop system, it's going to have this kind of thing in like where you repeatedly apply the control law rather than just apply it once. And so that's the general space of things we're going to cover. We'll talk about PID control, then pure pursuit, then a more general space of things called model predictive control, which means you're going to keep replanning. And then we'll have LQR, which is a special case, which is Gaussian and linear, and so on, right? So I think we've covered some amount of PID. You guys covered bang control, is that right, last time? And then we'll cover PID, pure pursuit, and so on. That's a strange name, I know. But yeah, so we'll quickly recap bang control, go through PID and pure pursuit. Yes? Tell me if my scoping is wrong because I wasn't here last. Yes? Okay. So bang control is really, really simple. It just says that if your error is positive, go negative. If your error is negative, go positive, right? So it's just saying that if you're this way, go that way. If you're that way, go this way. That's it. And you always set the actions to the max actions. And so you're always saying that if you're all the way to the right, you take the max action to go to the left. If you're to the left, you take the max action to go to the right. Now, what's tricky about this? What happens?
So as soon as you go across the line, it's suddenly have to turn, but you
Right.
shot.
Right, exactly. So you start having like behavior which looks like, like you kind of do this kind of thing, right? So you'll see like wild careening around, and you'll never like stabilize your system, right? And so stability is usually saying that you want your system to go to a fixed point, which is often set as 0, in the limit of time, right? So different types of control theory is all about stabilizing systems, and so you're trying to stabilize your system to the 0 point, and bang control is typically not stable, right? So it's never going to go to 0 error. And so the challenge with bang control is that if you run this control, you tend to have error that never goes to 0. You go too far to the left, you go too far to the right, you keep repeating. So, okay. If we were to fix this, how do we fix this? We want to, avoid this like unstable, back and forth behavior. What do we do to make it better? Thoughts?
Yes. As we get closer to the stable state,
Right.
then we need to correct less, I guess.
Yes.
We dampen off this.
So if you go back to this rule, what would you change?
Make that proportional to the error.
Make that proportional to the, right? And so the key point that Dhruvan is just talking about is like, right now what's happening is over here, we're applying a big force, but over here, we're also applying a big force. Whereas over here, maybe we need to only apply a little force. And when we're here, we want to really apply 0 force. Right? And so our 0 actions. And so what we're going to do in PID control is we're going to adapt the magnitude of our control proportional to the error, not just max this way or max that. Okay, so we want to do better, and that's where PID control comes in. So PID control is all about how do we build things proportional. It's called the proportional integral derivative controller. It's a PID. How do we like leverage the magnitude of error to control how we move, right? And so basically, maybe Tyler told you about this, but basically every control system almost every control system uses some type of PID somewhere. All our robots use PID controllers underneath. So even if you're doing deep reinforcement learning, there's still PID underneath in most cases, right? So it's useful to know. The caveats here are it's great in certain cases. Don't do backflips with a PID controller. It's going to lead to problems because it doesn't really capture dynamics in a very nuanced way. Right? So don't use it right. Okay, so the crux of PID control is that you're trying to choose a control law that brings your error to 0 and keeps it there. And so the first element of PID control, so PID controllers look something like this. It's going to be proportional term, an integral term, a derivative term, right? And so you can kind of think of this, it has a Christmas carol flavor to it. It's like a present, past, and future, right? And so you're like, this is your current error. This is the error that you accumulated in the past, and this is the error that you expect to have in the future, right? And so you can kind of think of this as like, it's very similar to a spring damper system. If you ever heard of those in physics, you can kind of think of these as different. This is kind of like your force, this is like your damping, right? And so it's got a similar flavor to spring damper. And you can kind of think of it as you're like, this is your set point of your spring. You're trying to design your spring so that it stabilizes like that, right? And so whenever you think of PID control, at least I think of it as a spring damper system. Okay, so we're going to have a proportional term, integral term, a derivative term, right? And so let's try to work through each of these, right? So the proportional term says let's minimize the current error. You have some error, you want to get back to this 0 point as quickly as possible, and so you're trying to minimize the current error. What the integral says is if you're accumulating error, try harder, right? So it means that I've tried pretty hard with my proportional term to get to 0. It's not happening. Try harder, right? It's saying, so the integral term is really connected to an idea called adaptive control. And adaptive control basically says that you have a control rule. If your control rule is not getting you to where you want to be, change the control rule, right? Whereas proportional control is not changing the control rule. The control rule is always linear in error. But adaptive control, it accumulates error, and so it's inherently adaptive. And derivative is kind of like, they're like brakes. It's like damping, saying that if I'm going too fast one way, just like slow it down and try to like not have wild instability in your control. So you can kind of think of this as like, you can kind of think of your proportional term as doing a lot of your heavy lifting. And then your integral term is trying to reduce steady state error. So reduce steady state error means that like if you're trying to converge to this point, you're not converging. What it does is it forces you to converge. And you can kind of think of your derivative as preventing this kind of like high frequency behavior, right? So it tries to penalize high frequency behavior. That makes sense intuitively? So it's PID. Let's go through each of these terms. So the proportional controller is saying that your action is negative KP ECT, right? Where ECT is your cross-track error, and you apply actions which are negative KP scaling of ECT. So it's linear in your error, right? But it's opposite to the direction of error. So you're saying that like your error here, you had some error right here. You choose your action. Let's say your error is negative here, right? Your action is going to be positive. Right? It's positive proportional to how big the error was. So it's going to be large here. As you go smaller, it's going to be smaller. At this point, there'll be zero actions, right? So if that was the case, I would expect that this thing would like go and stabilize here, right? Like why is it like this wave? What causes it to go? Causes it to go past? Momentum, right? That's it. So in most systems, you have momentum. It's not that zero error means that you stop, right? So you're going to go past. And so you got to have some feedback to correct for that. And so what the PID controller is going to do is going to send you towards the middle, and then you're going to have some momentum that'll carry you to the other side. Now your error is positive, which means your actions are negative, which bring you back to the middle. But now it's like, if you look at the amplitude of this, it's going to be smaller. And usually most of these systems will like have something that does like something like that. So it like goes to zero over time, right? And so in a certain set of conditions, you can show that the PID controller is stable, right? Okay, so this thing, KP, is often called your gain. Right? So let's try to understand what happens. You're going to tune the gains in your next homework. So what happens if the gain is really high? Yeah, it oscillates more. Right? It's kind of like, think of it as a spring which has a huge spring constant. It's going to go like, meh, right? And so if your gain is really high, you can think of it as your like force is going to be quite large, but because you have momentum, you're going to like overshoot more, right? And so you have a system that will tend to like overshoot that looks something like this and like have high oscillation, right? Whereas if your gain is low, it's kind of like a loose spring, and then you're saying that like I'm trying to go back to the middle, but I don't have enough force to overcome like my momentum, so I'm just going to like kind of swing around, go slowly, right? And so like you can kind of think of low gain as like not as much oscillation, but you're like slowly getting to the optimum. Whereas when the gain is too high, you get to 0 point fast, but then you oscillate a lot, right? And so that's kind of the way to think about the Peter, right? And so it's kind of like one way to think about it is if your gain is too high, it's kind of like a cat chasing its own tail. You just like you go here, and this guy sends you all the way here, and this guy sends you all the way here, and you keep going like that, right? So usually if you like ever run your systems and you find that it's just like not going to you find that they're jerky, like if you're running a robot arm, you find that it's jerky, try lowering the gains. But if you're finding that your arm doesn't reach where you want it to reach, then you up your gains. Right? So just like a simple linear tuning. Okay. That makes sense? The Peter. Any questions? Solid. Okay, so the next thing is the I term, which is interesting. So the I term says that it's an adaptive controller. It's the integral, which is saying that let's sum up the error over the past some number of time steps, right? And it's using something proportional to that error, right? So it's saying, again, it's negative Ki, but not times the current error, it's times the historical sum of the error. So why does that make sense? Like where would that help? Yeah.
Yes, the example that I gave yesterday was if you have a wind blowing against in the direction of the inlet,
Right.
then your current force is insufficient to get you back on track. So you need a front and back. You get off track. So
Right. Right. You can kind of think of it as like, okay, there is wind coming and your KP ECT is fighting the wind. Right? And KP ECT is doing its best to fight the wind. The wind is going this way, your air is going this way, but like KP ECT is going to like saturate at some point when this is equal to the wind, right? It's like if that force is balancing it out, it's like never going to get higher, right? So you're going to have some steady state error, which in like a chemical plant may mean that you just like get stuck at some point which is not your set point. Or a robot arm is like get stuck somewhere which is not the place you want to go because of like forces on your system, right? Or disturbances. And so what this guy is saying is now if you have like if this error is non-zero, let's say you had wind and KP fighting each other and this error was non-zero. So you have some non-zero steady state error. Like while it doesn't change over here, because this is a sum, this will keep increasing. Right? And the integral keeps increasing. That means this term will keep increasing until ECT goes to zero, in which case it doesn't increase anymore. Right? And so one way to think about it is just like this is accumulating error, and the only way for this to stop growing is if ECT becomes zero. Right? You can think of it as like area under the curve, and you kind of want the area under the curve to stay consistent. Right? Yeah.
There'd be like a certain amount of time that you look backward.
Yeah.
Back all the way.
Right.
You might end up.
Usually you'll have like a window you look over. And so usually you approximate this integral with like a numerical method. You'll just like sum up errors over some amount of time. And so yeah, exactly. Good question, right? And so what we're saying here is that if you have a system which has some steady state error due to a disturbance, what the I term lets you do is overcome that steady state error. Your I term is not going to like dampen your oscillations or anything like that. Your I term is really trying to say, hey, your output didn't converge to where you want it to be. And so it's going to give you that extra bit of juice that's going to get you to your set point. Right? And so like the way I like to think about it is like this thing is going to keep growing until your ECT is zero, at which point this remains constant, right? It's like an integral, which ECT, if ECT is zero, it remains constant, which means that this term doesn't grow, right? And so then everything goes to, like you stay at your set point, right? And so you can kind of think of it as a little bit of extra force. Now there's like more sophisticated ways of doing adaptive control. Like this is a linear way of doing it with an integral. You can also have like a nonlinear function, or like a lot of reinforcement learning is trying to get these kinds of adaptive controllers with nonlinear functions. Okay. But that's integrals, right? And then the last thing we have is the derivative. So that's kd times dot, right? Or E dot is the rate of change of error. Right? And so in some sense, the rate of change of error is telling you like, what is your predicted change in error at this instantaneous point? And you're trying to like penalize it, right? So if you're going like too fast one direction, it's going to try and like apply force in the other direction to slow you down, right? So it's kind of like if you're ever in like in a spring damper system, it's like the damping. So it's saying that hey, you're like zooming too fast to the middle, like chill out, slow down, right? So you can kind of think of an integral as a sum of things in the past. You can think of a gradient as predicting the future, right? So it's like the gradient is saying like this is a gradient with respect to time. So it's an instantaneous prediction of what the next step is going to be. And so you can kind of think of this as just a term which kind of prevents like big oscillations, right? And it's trying to get you to converge more smoothly to the steady state. And so like for instance, when you start, your derivative is almost, your error is negative, your derivative is almost zero, and your action is zero. Then you apply it in action, right? So your error is still negative, but your rate of change of the error is positive, right? And which means that like you're going to apply some KD force against that, right? So it's like this term is taking you this way, and this term is kind of taking you this way, right? So it's like fighting, it's damping against the like fast B term. You can kind of think of the KD term as just like something that like stabilizes your system, tries to get it to converge without as many oscillations. Right? And so it's like opposing the rate of change of the error. Right? So you can see that the error the error may be negative, but is trending positive, which means that your KD term is going to be going negative. Okay. So the question is, how do you evaluate the derivative term, right? So we're talking about a system that we're going to apply these, we're going to have to implement this, right? So how do we actually compute E dot? What does that look like? We want to compute the derivative term. The derivative term is KD times ECT dot. Remember, this is cross track error, right? So how do we compute ECT dot? Dot, whenever you say dot, that means like derivative of ECT with respect to time. So you want to compute the derivative of ECT with respect to time. How would we do that? Yeah.
Really basically take where you were some amount of time back.
That's right.
Predict that you will.
That's right. So it's numerical differentiation, right? So you basically say, hey, you were here at ECT at the current time step. You were here at like some time step before, right? Minus delta t. You take ECT minus ECT minus delta t divided by delta t, kind of gives you your derivative, right? So just a numerical differentiation. It's often called finite differences. You're just like taking a finite difference in time, and you can compute the gradient, right? So if you imagine you had a function, you want to compute its derivative, you can take this point, you can take this point, you can look at their difference, and like you look at their difference in value and divide by how different the points were, and that gives you the gradient, right? And so you can do the exact same thing here. But as I've written up here, it's not a great idea. Why is it not a great idea?
The rating where you want.
That's right. That's right. Your sensor readings may be noisy, this high variance thing. It kind of propagates, right? And so what we're going to do instead is we're going to analytically compute the derivative because we kind of know this system, right? So if you remember the way we computed it last time, you took x minus x ref, y minus y ref, and you had a rotation matrix, right? So you kind of know what ECT is going to be, which means that you can take its derivative, right? And so to take its derivative, you say that I'm going to just take the gradient of this thing with respect to time, right? And so you can kind of think of this as like some things here are constants, right? X ref, for instance, is a constant. Y ref is a constant, right? So you can say that the gradient of this thing is going to be minus sine theta times x dot from here is plus cosine theta times y dot, right? So you can say that, let's kind of work it out slowly. ECT is minus sine theta x minus x ref plus cosine theta y minus y ref, right? Or theta ref. Now this is a constant, right? So the only things that change with time are x and y. Yeah. And so what you'll get here is that if you take the gradient, it's going to give you minus sine theta ref dx dt plus cosine theta ref dy dt, right? And so that's the first step. And then if you remember what we did in the motion model, like dx dt was just v cosine theta, and dy dt was v sine theta, right? You're just like projecting the velocity along x and y. You remember the car was going like this, so the velocity was this way. You say that the change in x is v cosine theta, change in y is v sine theta, right? You just project it onto the right axis. And so the second step here is we're just taking x dot as v cosine theta and y dot as v sine theta, right? And so now, if you remember your trigonometric identities, if you ever have like minus sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2, that is sine of theta 2 minus theta 1. Just look it up. It's yeah, that's the identity for now. Yeah.
Are we
We're gonna assume a constant V for this. We're gonna assume that the V doesn't change within like one time.
But how are we getting that?
No, the V is a control. The V is something that you, like the V is the action that you're taking for your speed. So I guess it's not noisy actions. You may still have noise in the motion model, but that's captured elsewhere. Yeah, good question. Okay, so you supply your identity, you get V sine theta minus theta ref, right? So you're saying that's the like V sine of your error, right? Theta error is the difference between your current theta and your desired theta. Right, so the nice part here is that you can kind of replace your ECT dot. You don't have to do any numerical stuff. You can just replace it by V sine theta, right? And so when in your homework and so on, when you're doing PID error, just replace your derivative term with just V sine theta. So that's kind of why we're using the derivative term. Now, a challenge here is that as Marco was talking about, there's like potentially lots of noise and variation. And so what happens with noise and variation is it's like hard to separate signal from noise, which means that your gradient may appear really high, even though it's not, right? And so sometimes when you have like this kind of sensor noise or actuator noise, your D term leads to these huge control variations because your gradient is high, but not because the like system is moving too fast, more because there's just noise in the sensors. And so sometimes you like often you will like actually drop the D term because it's like sensitive to really noisy things. So in practice, a lot of controllers we use in the lab are just PI controllers and they don't always have the D term. Okay, so some intuition here is that your proportional term says minimize the current error. Integral says if I'm accumulating error, try more. And derivative says put on the brakes, slow down, right? So that's the whole of PID control. Questions? Yeah.
For defining the actual rotation based on like.
So you're only this is to control the steering angle. Right. So we're only saying yeah, you're only controlling the delta. Okay. So now we've talked about these three terms, but they have these coefficients Kp, Ki, and Kd, right? Those are called your gains. The natural question becomes, how do you tune these constants for a particular system? Right? So you can do the brute force method. But it's good to keep these intuitions around, right? Like if you're finding that you're just not getting to the point you're at, up your I term. If you're going too fast and oscillating, maybe increase your damping term, right? But in general, there's like a bunch of literature on this. We're not going to go into too much detail, but one of them is called the Ziegler-Nichols method, where they have like a heuristic rule that looks something like this. It's like totally heuristic, just done with experimentation. But the procedure kind of looks as follows. You start by just setting a P term. You set Ki and Kd to 0. Right? And what you're going to do is you're going to like allow your system to go to a steady state and kind of oscillate, right? And then what you do is that you set the command to a step function or to 0. You kind of increase the Kp term until your system goes and like oscillates. You use that to determine the frequency of your system, and that is used like with these rules to set your Ki terms and your Kd terms. Right? And so I don't know if I have a great explanation for it, except they tried a bunch of shit and one of them worked, and that's it. But there's a bunch of methods like this that allow you to tune the PID controller. So in your homeworks, if you're feeling adventurous, try it out. Cool. So that is PID control. How do you feel about it? Easy peasy? Good. Alrighty. So the next thing we're going to cover is this thing called pure pursuit. And so pure pursuit is something called like lateral vehicle control, but it's a way to control these kinds of specific vehicles like cars and planes and so on. But you can kind of think of it as your like the analogy they like to give is like a carrot on a stick. You just set up a target, you're trying to go towards the target, and then you like move the target. It's just like you're always chasing a carrot on a stick. So you're giving yourself a target in front, trying to reach it, then the target moves, you're trying to reach it, you're trying to like, follow a goal all the time. And so an analogy the original paper talks about is you're following an aircraft and you're like pointing your nose towards it, the aircraft moves, you point your nose towards it and repeat. So it's literally pursuing. And why do we need pure pursuit? Well, the problem with PID control was that it like did not use the model at all. It's like you can apply a PID controller to any system, right? So if you look at PID control, there's nothing about the model. Like it only has to do with the error. It's just saying it's like a heuristic line follower. You're this way, go that way. If you're this way, go that way. But it doesn't use the model at all, right? And so what pure pursuit is saying is that, hey, you're in a system where you know the model. Why shouldn't we use the model, right? If you have the model, use the model. Whereas with PID control, you're saying, hey, it's really general. It works across lots of systems, but it doesn't use the model. And so the motivation behind pure pursuit is let's build a rule that like follows paths for the car. It may not work for other systems, but it'll work for the car. Okay. So the key insight here is the car is always just moving in circles, right? And so it's really just leveraging the fact that if you remember the way we derived our motion model, like the car just tends to move in a circle, right? So if you remember, there's like an instantaneous center of rotation. So if a car is translating and rotating, you can think of it as rotating around an instantaneous center of rotation. And so you're just going to leverage the fact that the car moves in circular arcs in order to like navigate places, right? And so one way to think about it is that you have a path, right? So you have a path that you're trying to hit. Let's say this was your point that you're trying to hit, right? What you can do with your controls is you can change the radius of this circle, right? And you're trying to change the radius of your circle so that your arc intersects with the point that you care about. And so all that pure pursuit is trying to do is trying to determine what is your angle of steering. What is what is your angle of steering so that your circle that you're going to make with your car is going to intersect with your lookup point, right? And so all that it's trying to do is inverse solve for delta such that the desired radius kind of hits the lookup point, the reference point you're trying to get to. Right? And so all we're going to do is a bit of geometry to get the radius of the circle that'll get us to where we want to go. Right? So let's consider if you remember how we did look ahead, like we were trying to choose a point that we're trying to get to, which is not the nearest point, but a little look ahead. We can say that the distance between x and y and x ref, y ref is equal to L, right? We're saying we're going to look ahead. We're going to look ahead to a point which is like a distance L away, right? Just to avoid notational confusion, let's call it like LD, right? Because earlier, if you remember, we had like the car of length L. So we're gonna, let's say we call it LD. So how do we choose this? How do we choose a steering angle that like gets this guy to go through here? Right. So you can kind of think of it as you choose a lookup point, you get a steering angle that goes through here. Now, once you're here, you choose a different steering point, so you kind of go through here. So here, you have a different steering point, so you kind of go through here. Right. And so you can kind of think of it as it'll do something like whatever, like that. But it's using the like specific model of the car to do it. And so the idea here is we want to solve for an arc that passes through a look ahead point, right? And as we move forward, the point is going to keep moving. So it's not that we're going to go here and stop. It's more that we're going to go here, move a little bit, the point changes, move a little bit, point changes, move a little bit. It's going to be relatively smooth. Okay, so we're going to keep changing the look ahead. That's going to kind of keep us on a path that looks like this. So the procedure looks like find a look ahead, compute the arc, move a little bit forward along the arc, right? Let it happen for a little while, and then go back to step one, recompute your look ahead, compute your arc again. Okay, so what we're going to try and do is we're just going to do a little bit of geometry that takes our car like through it's going to choose a radius that is going to take us through a particular look ahead point. Yep. Okay, so let's start by like reviewing our motion model, right? So if you remember our motion model, if you're trying to find the center of rotation, right, we're going to say that like, hey, your velocity was v, your theta was the angle that your car is currently making from the x-axis, and delta is your steering angle, right? So we said that, hey, like x dot is v cosine theta, y dot is v sine theta. Theta dot, which is the rate of change of theta, is v over r, right? So this is the angular momentum, which is equal to your velocity divided by your radius, right? Radius, which is the distance between your car and the center of rotation. Right? So those are things we already did. And when we worked through some algebra here, if you remember, we just like, we worked through some algebra. We just said this was delta, this was 90 minus delta, this was delta, right? So we remember, if you remember what we did, we said tangent delta is equal to L over R, which means that R is equal to L over tangent delta, right? Which means that the radius that you pick is dependent on the length of your car and the choice of steering angle, right? And so what we're going to try and do now is we're going to try and choose an R that gets us to a particular point, right? Or we're going to choose, rather, we're going to choose a delta that gets us to a particular point, but delta directly controls R. And so we're going to try and solve for the delta, which chooses the right R, which gets us through our point of interest. Does that make sense? Okay. So remember that we're gonna tangent delta is equal to L over R, which means that R is equal to L over tangent delta. We're gonna try and solve for delta, right? So we're trying to do, if you remember the motion model, right? The motion model was saying, given a control and a velocity, what is the next state? Here we're gonna do control, so we're saying, given a target state, what is the right delta? That's just the opposite of a motion model. So you can often think of control as like inverting a model. The model takes a control, tells you what's going to happen. Like controller is going to take a goal and give you the right control to make it happen through the model. Right? And so in general, even beyond pure pursuit, think of planning, think of control as just like inverting a model. Model goes forward, planning goes backwards. So planning takes a target and gives you the control. Planning and control both do the same thing. Okay, so we know that R is equal to L over tangent delta. And we are going to try and figure out, like, in our case, how do we choose delta to intersect with our point? Right? And so specifically, we're going to say, hey, our car is here. We want to get through some x ref, y ref, right? And like, we're going to try and decide what the delta is to get there. And so we're going to do a little bit of geometry here. So this figure is a little hard to make out, but let's think of a car like this. This is your reference point. You want your arc to go through your current car and go through your reference point. And you can kind of think of it as like there's an instantaneous center of rotation, right? So we know that, let's call this distance capital L, which is your car length. The distance between your car and the reference point, let's say, is L. And let's say your reference point is x ref, y ref. And this radius is R, called RPP, R pure pursuit. Okay, and so now what you can do is you can draw like a, right, like a perpendicular line, right? So like right now, like these two lines are not perpendicular to each other. They're like two radii of your circle, but you can draw a perpendicular line, right? And let's call this A, let's call this B. Yeah. And so what we're going to try and do is we're going to try to express RPP in terms of A and B. And then we're going to try and solve for A and B. So here's the logic, right? So we, in our previous slide, we try to get tangent delta in terms of L and R, right? Now, but we don't know R. So what we're going to try and do is trying to write R in terms of things that we do know, which is X, Y, the reference point, right? And so we're going to try and express r in terms of x, y, x ref, y ref, so that we can solve for delta, right? So the logic we're going to follow is we know from our motion model that tangent delta is L over r. We're trying to find the right r to get us to the reference point. And so we're going to solve for r in terms of x ref, y ref, x and y. And once we can solve for that, we substitute that into here. And you can directly get what delta is going to be, right? And so you try to substitute, you try to get this thing into all known quantities, and then you know how to compute the control. Yeah? And so you can think of our logic here as we are trying to say tangent delta is equal to L over R. We don't know what the right R is to get us through the point of interest. We're going to solve for R in terms of x, y, x ref, y ref, right? And then we can substitute that into here. You can just take inverse tangent that gives you the steering angle. Right? That's our control rule. Yeah. I guess we're dealing with vectors, right? So we could just, I mean, it's like your subtraction will just have the opposite sign, but like symbolically it'll remain the same. Right? Goes this way or that. Yeah. Good question. Okay, so we're going to call this thing A, and we're going to call this thing B, right? And the first thing I'm going to try and do is I'm going to write RPP as some function of A and B. Okay, and once we write it as a function of A and B, we'll solve for A and B in terms of x ref, y ref, x and y. Okay, so the logic is we know that delta is equal to tangent inverse L divided by R. We're going to solve for R as a function of A and B. We're going to solve for A and B as a function of these four things. And now you get delta as a function of everything that you know. Okay, okay, so if you think of this as A and B, and this is like a right angle triangle, right? This little piece over here is RPP minus B, right? This thing is B. This is RPP minus B, right? And so now you just do like Pythagoras theorem here, which tells you what? Help me solve it. On this triangle. A squared plus B squared equals C squared. So A squared is going to be A squared. B squared is going to be RPP minus B, the whole square, is equal to RPP squared, right? So let's expand it. RPP squared plus B squared minus 2 RPPB is equal to RPP squared, right? Cancel, cancel. Now move this thing over to this side, which says A squared plus B squared equal to 2 RPPB, okay? Which means that B is equal to A squared plus B squared by 2B, or sorry, RPP. RPP is equal to A squared plus B squared over 2B, right? So you're expressing RPP, the radius of your circle, in terms of A and B, right? So once we solve for A and B, we know what RPP is going to be. Once we know for RPP, we stick it into like delta is equal to tangent inverse of L over R. Yes? So now we know that RPP is A squared plus B squared by 2B, and delta is equal to tangent inverse L over R, or RPP. So you just substitute this guy in here. We just need to solve for A and B. Yes? Bear with me. Just a little geometry. That's it. Okay, so we typeset that. You get RPP is A squared plus B squared by 2B. And now what we want to do is we want to write A and B in terms of x ref, y ref, x and y. Yeah, and theta. So the way we're going to do it is a little bit of like change of frame of reference. And so you can kind of think of it as take this whole thing and just like rotate it. And so rotate it so that the car is facing like vertically up. And so you can kind of think of it as like rotate this whole thing counterclockwise. And so the whole system starts to look like this. This is your car. This is where you wanted your car to be. right? And so you're trying to follow this arc here. But if you like rotate this thing, you're going to have like your circle, same as before. This is going to be L, this is going to be R, this is going to be A, B, and RPP minus B, right? So just think of like rotating the whole frame of reference. The reason it'll just be easier to compute A and B, right? And so one way you can kind of think about, like, in this frame, if you had converted to this frame of reference, right, then it's just like the difference between x and extra, x and xref, xref and x, yref and y, and you're just going to rotate it, right? Because in this frame of reference, b is the difference between these points, and a is the difference between these points, because like axis aligned, right? And so an easy way to think about it is that you're going to take the difference between these points, right? And then you're going to rotate the whole thing. Tyler talked about rotation matrices last time, right? Yes? Okay, so you can kind of think of this as like, take a vector, which goes between here and here, and then just like rotate it. And once you rotate it, the x of the vector is going to give you b, and the y of the vector is going to give you a. Right? And so, like an easy way, like we know the rotation matrix, right? It's like cosine theta, minus sine theta, cosine theta, right? You're just going to substitute in minus theta because you're rotating this way into here. And you know xref, you know yref, you know x, y, you know theta. Right? And so you directly get what A and B are. So you can stick A and B into here, and you can stick that into your controller, right? And so, see, do I have a typeset here? Okay, so let's put all the pieces together, right? So we said that tangent delta is equal to L over R. Right? If you remember, we just did like a little bit of geometry. So say this is delta. The tangent delta is L over R. We didn't know what R was going to be, but we said R is A squared plus B squared by 2B. Right? And if you think of this thing, it's A squared plus B squared by 2B. We wanted to compute A and B in terms of these things. And so you can say A and B is cosine theta, sine theta, minus sine theta, cosine theta of x ref minus x, y ref minus y. Just going to rotate it, right? And that's going to give you A and B. You can get A and B, stick it into here. You can get R, stick it into here. Take inverse tangent, it gives you the steering angle. Right? But you've like solved it analytically, and it's using the model of the system. So it's using the fact that it's like a car, right? So if you look at like all of these videos I showed you at the start, like the DARPA Grand Challenge and the Urban Challenge, like a lot of them just use this controller. So it's like not just a toy thing we made up, it's like a thing that people use in practice or have used in practice. Cool. Does that make sense? We went through a bunch of geometry, but really just think about it as like you are trying to choose the radius of the arc that gets you through the point, right? And you're just trying to solve for what R is going to be. You solve for it in terms of A and B. A and B is just take the difference and rotate it with your rotation matrix. Okay, I think we're out of time, but I will see you guys on Monday. Thanks. Was the talk? They're all recorded. Yeah, yeah. Just go to the UW CSE page and they're all on there.